Hello YouTube, and welcome to my video on the project review and evaluation technique, also known as PERT. And in this quick video we'll be just going over why you'd want to use PERT, how do you get started with it, and also how we can actually start coding up a model using Python for PERT so you can start doing your own analysis. So if we go to the definition from Wikipedia, the PERT technique is a method for analysing the activities involved in completing a given project, especially the time needed to complete each task, and to identify the minimum time needed to complete the project. So that's straight from Wikipedia, and PERT takes this kind of graph-based approach where your activities are nodes, the edges are dependencies between those activities, and you have the times needed to complete those activities. We can then traverse that graph to identify critical paths, critical activities, and slack between them. So that nicely takes us on to what can we get from it? Well, just as I said there, we can identify the expected activity times, how long activities are going to take. We will look at identifying float and slack, which is the excess time and resources available to complete activities, enable that maybe to be shifted along the time schedule, the project schedule, so you've got some freedom in those. We can look at critical paths and critical activities, the ones that can't be shifted or can't be moved if we wanted to complete the project on time as planned. We can look at lead times and lag times between projects, and also do fast tracking, seeing if there's any critical activities that are running in parallel. So what do we need to actually start this analysing our projects through PERT? Well, the fundamental bits of information that we need are information about our activities and a plan of how they fit together. So PERT normally goes in hand with a work breakdown structure. Once you've identified your activities and their dependencies, you can then work going into using PERT to analyse the likely time needed to complete all that work. So we need to define the activities, so they need to have ultimately a unique identifier for the activity. You'll probably also have descriptions and other descriptive details alongside that. We need to know the dependencies, so basically which unique IDs and activities the activities are dependent upon. And then we take 3 times, an optimistic time, what we feel is the minimal possible time required to complete the activity, what the most likely time we feel that the activity will take, and then a pessimistic time, what happens if we had a few issues or things go wrong, what would be the possible worst case scenario, exclude any major project issues. So in this video we'll just go for this example of a set of nodes, set of activities, neatly named A, B, C, D, E, F and G, with SOP meaning start of project, EOP end of project, and we've identified the optimistic, most likely and pessimistic times. And what we want to do is create that graph network, traverse it, get those metrics out. So how we're going to do that, we're going to go and code that up using Python, using VS Code, and I'm using Windows Subsystem for Linux as the environment to run the Python in. There's many ways we can run it, but that's the setup that you'll see today. So our first step will be representing the project plan in code form. So here's a diagram of the project and the dependencies between the activities. And in these boxes we'll be wanting to identify the early start time, early finish times, durations, late start times, the float, late finish, and we'll be going through that in this video. But first of all, we just want to create this kind of network in code and have our activities represented in code. So let's start with doing that in Python. So here we go, I've got my Python editor up. Here we go, VS Code. So I've got a couple of things already set up here. I've got some settings with how I want to run Python and VS Code with Python, how it might format on save and organize our imports, do some type checking for us. I've also already taken those activities from that table and I've put them in a JSON file here. So here we've got a key, which is our unique identifier. We've got a list of dependencies, and we have the optimistic, most likely and pessimistic time. So those are those central features so we can start our PERT analysis. So it's just a list of all our activities in our project. And now we've got our empty main file which we can then start actually then importing those activities and creating our PERT model. The first thing we want to do is probably import those activities and represent them as a class within Python. So first of all, I want to do is have a typing or for that activities JSON file. So I'm going to create a class and call it activity JSON, so I can get my nice syntax highlighting and expected variables from my JSON file. It's going to be a class of a type dict because it's just doing typing for our JSON file. So just do typing, import type dict. There we go. So that's inbuilt package in Python. And actually through this demo, we're just going to be using all the basic inbuilt Python packages. That's it. So there are PERT packages and PERT software out here, but I thought it's just nice to show actually you can just create your own model from scratch using all the inbuilt tooling that Python provides. So here's our class activity JSON. As we mentioned in the activities JSON file, we've got the key, so that's a string. We have the dependencies variable, which is a list of strings. The optimistic time, and that's going to be a float. We're going to pass it as a float when we import it. We've got the most likely time, and that's also a float. And we have the pessimistic time, which is also a float. So that's what we're going to import from our JSON file. Okay, so I've got my previously done solution here. So first we go if name equals main. So this is going to be our runtime when we run this file. And if you're familiar with Python, you'll probably see this before. That's when you run the script, if it knows that this is this main script that you're entering, it will run this code. And what we're going to do is create, we're going to import those objects from the JSON file. So we want to do with open, activities.json. So we're going to just give it the JSON file as data. So it's just our data file. We're going to do activity data equals, we need to import a new package here, the JSON package. Import JSON. And we do JSON.load the data. So we are opening the file, giving it to the package JSON and its function load, and it's actually going to load our data into that, and that is actually of type activity JSON. So we can already here it's implicitly saying it's of a type any, but we can, because we know ahead of time of what that type is, we could do this as a list of activity JSON. So that'll give us our syntax hinting. So that's loaded in, and what we want to do is then for each of those objects, we want to now create another class. We're actually going to then implement it with a set of functions that are going to be doing our PERT analysis for us, and that's going to be a class called activity, which is going to be our base class for our PERT model. So we're going to create a new class called activity, and this is going to have all the variables, and some of the variables I mentioned earlier here, the early start time, duration, and early finish. And we're going to put those all into our activity class. So we're going to say we need our string, because key of the string, our unique ID. We're going to, actually I'll just copy and paste these up from up above to speed up there. So we're going to also, bring in our dependencies. We're going to have the optimistic time, most likely time, and pessimistic time, all the things that have come from our JSON file. It's going to be in our activity class. And we are also going to then compute some variables. So I'm going to just put a note here that we're going to compute these variables. And what we're going to do is we're going to have some from activities. So we're going to start building this network. So this activity is going to be dependent on some coming from it or going to it. So this is going to be a list, and we have to do quotation marks here because we're forward referencing the type of activity. So it's going to be a list of activities. We're going to do 2 activities. So yeah, we're coming from, and then we're going to a set of activities, and that's a way of us being able to navigate and traverse the graph that the set of activities represent that project plan. We're going to compute something called the expected time, as we mentioned in what do we get from PERT. And that's a float. We're going to compute the early start time, the earliest start time that we can start the activity. We're going to do the early finish time. That's the earliest time it's going to finish, and then same again for the late start time. Oops. And late finish time. Okay, and then we've got a couple more ones, which is then slack, and I'm also going to add a variable is critical. So we're going to traverse this path, and once we identify the critical items, we're going to set them as a bool to say, hey, this is a critical activity, so we can quickly loop and pull those out of our list of activities that we're going to have. So what we need to do is be able to define it now. So actually initialize it, and we use our def init function to initialize this class. And what we're going to accept is the JSON object, activity.json. And we're also going to accept what we're going to call it the project plan, which is going to be our collection of activities. So that's going to be a dictionary of string, and again forward referencing of type activity. So it's going to be, that's going to be the full list. In this, then there'll be a lot of self key defining here. So this is going to link to our JSON file, and as you can see now, because we typed it activity.json, we get the syntax highlighting there. So that's going to be our key. We want to do our dependencies, which are going to be related to dependencies. We're going to do our optimistic time, which is also in our JSON object. Optimistic time. We're going to do our pessimistic, most likely time, and pessimistic time as well. So bear with me as I code these up. Oops. Most. Oh, it's not doing my syntax highlighting. Try this again. There we go. Self.pessimistic. JSON. There we go. And then scroll down to pessimistic time. So we've added all of those into our activity. We also need, and I forgot to add, is a reference to our project plan. I'll have that. So the activity knows about the project plan as well. Almost the global list of activities that it could be related to. I'm going to just put that up here. Okay, and again forward referencing there, so it's just exactly the same as this project plan here. We need to make that link in our init when we initialize the activity. And one of the first things we can actually do here is create our first calculation, and one of the first aspects that we can get from PERT, and that is, if I come to here, calculating the expected completion time, which is the optimistic time 4 times the most likely plus the pessimistic over 6, and that gives us our expected time. So now we've got all those variables, we can easily compute this, and we just do dot expected time is self.optimistic time plus 4 times self dot most likely time plus self.pessimistic time divided by 6. There we go, and it's just done the formatting for us. And then we want to do set defaults for all the other variables, which we will then backfill once we do our model and we'll run our PERT model across all our activities to work out early, late times and slack and critical paths. So we need to do self.from activities. I'm going to say it's empty for now. Self.to activities, it's empty now. Self.early start time is 0. Self.early finish time is also going to be start at 0. Self.late start time. We're going to set this as a really high value, and we'll see this in a moment, that for the early start times we will propagate forward through the network, and for the late start times and calculations we'll propagate backwards. And we'll be using a set of recursive functions to do so. So we've still got self.slack, which does 0, and self.isCritical. We're going to set that to false, so none of our variables are going to be, any of our activities are going to be critical by default. And now we can then return the activity. So right, so we need to now actually create our project plan and then load those activities with their class into that plan. Oh, I've moved across, there we go. Okay, so let's create our global project plan. And it is of the type, I'll just copy it across, the dictionary. So the string is going to be the key, and the activities, as I say, it's the activity. So it's going to be just empty to start with. So I'll just scroll with my demo on the side here. Okay, so we've loaded those activities in. Now we need to loop through all those JSON objects. So we can call them for JSON in activity data. And we can create the activity. And we're going to give it the JSON for JSON. JSON. We're going to give the project plan. Okay. Like I said, we don't actually return. We don't actually return the activities. We don't need this actually, because we never return an activity here. We could return self, but because we're connecting up with the project plan, we're going to actually interface with them through the project plan again. So that's how we can grab access to them once again. But you could return it and use it as well. So that's us setting up those activities. So now we have a dictionary list of keys and activities, but they're not linked together. We haven't done any of the from or to the activities, so there's no network as such. They're just this list of activities in a dictionary. So what we want to do is do our connectivity loop. So what we're going to do is we're going to create a function that's going to connect all these activities up, and we're going to put it in the class. So we're going to run through each activity and ask it to connect to the activities that it's identified in its dependencies list from the JSON object. The reason why I do it later rather than do it on initialization is that not all the projects, all the activities are active. Not all the activities are in the project plan. So we need to wait till the project plan is fully instantiated with all the activities before we can then start doing the associations and effectively create the edges in our network. So what we want to do here is connect, and I'll just scroll up here. Okay, let's type self. It's going to need itself. It's going to return none. It's just going to be an internal update. What we're going to do is go for key in self.dependencies. So it's going to look for the dependencies within itself, and if not in self.project plan, we're going to do a little check here. So this check is just saying, yeah, we should expect to see all the nodes in there. But if not, we're going to say node does not exist. Well, we should actually probably just keep it simple and say activity does not exist in project plan. And we'll exit the application or the runtime there, just in case there is an issue there. It should be okay. What have we got here? Oops. If key, sorry, not in. Getting ahead of myself in my typing. Okay, it'll exit. So what we're doing there is going through the loop of dependencies. We're going to see if their key is in the project plan, therefore the activity exists. And if so, we're going to do self dot from activities dot append. So these are the ones that it's dependent upon, and we're just going to grab the reference from our project plan. And same again for project plan for the key, for the key that we're the activity that we're related to. We'll do it vice versa, so it's got it in its two activities, so we can go back and forth between the activities depending on which way we want to go up and down the network. And there we go. So that's us connecting our projects together. So now we just do for activity in project plan values. So our project plan holds all the activities. We are going to then do a.connect. Oops, activity.connect. So there we go. So that should then loop round and connect all of our activities together. And we can run it now, and it shouldn't really show much. We could print out the activity data just to showcase what we are, what's happening as well. So let's just check everything's running as expected. Oops, -3 of course. There we go for me. There we go. So yeah, this is just printed out that activity data, and it's gone on and created those activities and connected those. We could see if we printed the project plan and see what this shows us. It should show us that, oh, it's an empty project plan. Let's just see what keys are in there. I might have not associated. I know what I haven't done. Yeah, so it's an empty project plan at the moment because we've sped across and we haven't, let's close those prints, we haven't added the actual activity itself to the project plan. So we need to set the project plan. We can do it is self.key. So we say, yeah, this is us. So hopefully, if we do our activities now, whoops, I've lost the prints there, so we can print this back out. So if we do project plan.keys, we should, oops, get a list of our dictionary keys. There we go. So there we go. So we have now connected our project up. So we forgot that last little trick there. Once I've instantiated it, the last step there was just to make sure that I reference myself in the project plan. So there we go. That's our list of keys in there. Okay, so now we've done that, and we've done the connections as well. So if you wanted to take a look at a project and what it's connected to, let's just, one thing we want to do is probably, the challenge here is that because we're doing a list of activities, we're doing a lot of self-referencing, and when you're printing it out, it can get quite messy. So I was going to just do a quick def represent function, so how we want to represent the activity class when we want to print it out to screen. So this is an inbuilt class that we could override, so it's represent, and this is going to show this is the string that when we say print this activity, this is what it should look like. What I'm going to return, and I'm going to use, and I have to import this, is p format from pretty print. So from pp print import p format, and this is going to format ourselves the variables of self. We're not looking at functions, we just want to see these variables, and we're only going to a depth of 1, so if it starts traversing, it won't endlessly traverse down a set of activities because of this potentially networked, circular network nature of our project plan. So we're just going to a depth of 1. So if we wanted, for example, to print project plan, that's the SOP, the starter project, then this should give us the variables and keys values for those variables. So we just run that, Python 3 main, and here it is. This is our SOP startup project. And so, of course, it has no times, and it has no from activities, which you expect, but it does have, and it's just hidden them, a set of 2 activities things to go to. It shows that it's linked to the project plan, and yet all of these are yet to be computed. So it's all looking good. So next step is to, of course, we want, because we might have that data is coming in and we've manually inputted it, we might want to put some checks in there to see whether we've wrongly connected some of the items up, or some of the paths do not lead to the end of project. So here we go, we want to check that the starter project has no dependencies. It should be the starting node. End of project should be connected but have no, it should be not going to anything else. We want to check all the paths lead to the end of project, so all of them somehow, that you should be able to go through your nodes and end at the end of project. We want to check there's no loops, recursive loops, so you're not having to revisit activities, and there could be many more. So those are a few that we're going to add in this demo. So the first one is to say, well, we'll do some checks. That let's just check that SOP, we expect that key to be in there, so we expect to start a project in our project plan, and if not, we're going to say, print expected and SOP activity. I can exit. Oops, I've done that again. If locked in. Okay. And if, again, we could do the same with EOP. Not in project plan. And again, I'll just copy and paste this on, so we can say expected an SOP activity, and we expected an EOP activity. And then we said about these idea of, we expect that there's no the end of project and start of project shouldn't have any like the to and from activities. So one we can check is the end of project. So if we do EOP, got 2 activities. The length of that, if it's greater than 0, then we know again we've connected up our plan wrong, or we might have written it wrong in our JSON file, and we could print out a useful helper to say EOP should not have any 2 activities. And we can exit that. And similarly for the start of project, but that will be for the case of from activities. So we'll just change here to SOP, and we'll do from activities, and we'll just change that to SOP should not have any from activities, and we'll exit again. So now we kind of say, okay, you've done some checks there. The one thing we want to do is to check that all paths lead to the end of project and there is no circular paths. To do that, we're going to start at the starter project and try and traverse through our network to the end of project. And what we're going to use there is a recursive function that we're going to hop then across all the activities, and hopefully for each one, even with the branching, we should then end up at the end of project activity. So we are going to help ourselves by just creating us a link or pointer to the end of project activity, and we're also going to create a link to the start of a project and end of project activities there. So they're just some useful variables because we want to use them again. And we will now create the project or the function all paths lead to EOP. So I'll scroll back up to the top here, and I'll create a function here then. All paths lead to EOP. Oops, I'm already putting in our variables there, so I'll just scroll up here. Okay, so what we want to do is have the path that we're going to store to show what the function traversed over time, and that's going to be a list of strings, and those strings are going to be the actual keys, the unique IDs of the activities, and we're going to have the activity that we're going to be going from, and then we're going to move from and move to. So this is the activity, and this is going to return us a list and a list of strings, because we're going to be recursively entering and maybe branching off. We're going to have a series, potentially a series of paths returning to us. So that's what we need to set up here. We don't need these return function just yet, because we still need to write out the entire function. The first step is if the activity dot key is in the path. So if it's already in the path, then we shouldn't have ever come back around. If we've come back and met the same activity again, it's likely that we've got a circular activity there. So we might go print may have a circular path, and we will want to exit there. If we haven't seen that key before in our path, then we can do path, we'll append it to the path, append our activity.key. So we've moved along the path 1. And if the length of activities, two activities, equals 0, oops, too many brackets there, we are going to say that we've reached the end, so we can return that path. Okay, so just do, and we're going to do it as a list of paths. There we go. So we're going to return that path because we've reached, we can't go any further. It should be the end of project. If not, we're going to then create a new variable called paths. So this is going to go, okay, so we've got some other activities to go to. So let's go and loop through those and do this function again. So so we call it next for the next activity. Let's do it, next activity. Oops. In activity.toActivities. We'll go paths.extend all paths lead to EOP. So path.copy. So what we're doing now is they're going to say, okay, now run it for this next activity. We're going to copy the current path that we've got, so it gets a nice fresh one that you can append to, and then we can start building up a list of paths, and we're going to give it the next activity to run through. And once it's done all that, it will return that set of paths to us as well. So this idea is that we're traversing. When we reach a node, if it branches, we'll run go down those branches again. If we run to one that has no activities to go to, then we'll return the path entirely. So that is our recursive function to start with, well, from a place, and it will be the start of project for us, and we want to get to the end of project. So hopefully all these paths will do. So let's call it and see what those paths are. Paths equals all paths lead to EOP, and we're going to give it start off with a blank path because we haven't traversed anywhere yet, and we're going to give it the SOP activity. That's going to be our starting activity, and then we could print these paths to see what we get. So fingers crossed, if it's all coded right, we should just get probably 3 paths, I believe it was. There we go, traversing our network. So if I go back to our figure, we should be going A, B, E, G, E, O, P, A, S, O, P, A, C, E, G, E, O, P, ADF EOP, and I believe ADF GOP, and yep, those are the same as those 3 branches that we've got in our project. So yep, we are traversing that path. They all end up at EOP, so we could put a check in there to say, if I go down here, so maybe go for path in paths, if path the final value is not equal to EOP, then we want to print path does not end on EOP, and maybe exit there so we can then start looking at debugging what that issue is. So that should just run through without any issues there. That's just good. And the other thing that we can do is make sure maybe we've added an activity that never gets visited, and maybe we've got this kind of like satellite activity or a set of 2 plans potentially in our project plan. So we would just want to make sure that all the activities were visited. So to do that, we're going to condense all those paths, make a final list, and hopefully that list will match the list of keys that we've got. So activities visited across all our paths will be, we're going to create a set, and we're going to use itertools .chain.from. I need to import this in a second. Iterable. So we're going to iterate all through the paths, and we're going to create a set of unique unique keys, because we might have duplicates depending on the path branching. We'll import itertools there, so that helps us just effectively condense those list of lists to a single set of unique items. And then we could do a quick check to say if activities visited is not equal to the set of project plan.keys, then we can say print not all activities have been visited. And again, we can debug, maybe look at our JSON file to see if we've incorrectly related the dependencies there. So if we just run this, it should just pass through because we're okay, we have visited all of them. And now we can get to the stage of, like, we've done some validation now, we've created the network, we're confident that it's representing the network we want. Now what we want to do is actually start doing some of those computations that we can get some valuable information out of our PERT analysis. So the first thing we're going to do here is early start and finish times. So again, we're going to use a recursive function. We're going to start at SOP, and we're going to traverse down through our network, calculating the early start times and early finish times, and then all end up at EOP. So what we want to do is create another function at the top here, and we're going to call this evaluate early start early times, I think, because it's both early start time and early late time. What we want to do is have a starting activity. So this is going to be our from activity. And because it's going to be of type activity, we're going to return none here. The function is just going to run. The values that are going to be updated are within the activities themselves, so we're just going to have to look at the activity objects to see what the values have come out as. It's not going to return the list. So the first thing we want to do is if length of from activity to activities is equal to 0, so i.e. there's no other activities to go to, we'll just exit our function. If there are 2 activities to go to, then we want to go to those, and then we'll do some calculations based on our data on early start times versus their data of start times. So for 2 activity in from activity dot to activities, it's a bit of a nested statement there. What we want to check because we may visit these nodes multiple times, so we want to check that the from activity dot early finish time is greater than or equal to the to activity early start time. If it is, we need to almost imagine you need to shift that node back a bit in space because it's starting too early. So we're going to shift it along, let's say the timeline. To do that, we're going to then say the to activity early start time is going to be equal to the from activity early finish time. So it can start as soon as the other one finishes. And the to activity dot early finish time is then going to have to be computed as the to activity dot early start time plus the to activity dot estimate expected time. So we've computed that expected time earlier. Now we're just moving on, so we can calculate the new early finish time for that activity. And because we're on that activity, we can go down the next stage in our graph and evaluate the early times following that node to activity. And that should then traverse all the way to our end of project and exit when we reach it, updating all those values for us. So all we need to do then is add it into our script. And we should, if I then print, because I've got access to the EOP, end of project, we'll be able to, we need to give that the SOP place to start from. If we print end of project, we should see that the early start times would have been updated on that activity. We just run that in here. And as we see here, we have now an early start time and early finish time of 19.5. So it's gone through all of those. So all of the activities do now have a early start and early finish time in their node, as it were, in their class. So that's early start and early finish. And like you see, it's just calculated by early start time plus the expected time of that activity. Now we want to do the same again for late start and late finish times, which is actually what we're going to do is then traverse this network backwards, start at end of project, move to start of project. And also we need to copy over at the end of project the early start time and finish times to the late start time and finish times and use those as the starting point. So, and this is where we need that high value, because what we want to do is, rather than moving forward in time, we're going to try and push these nodes backwards in time. So if it's a higher value, of course, we want to go, oh, no, we've got a lower value. We're going to move you back in the network. So we've printed that. So what we need to do is update EOP. Late finish time equals EOP early finish time. And EOP dot early late start time equals EOP dot late finish. Late start time. Given that EOP has no expected time, you can use them. Could use them alternatively anyway. Early start time. No. There it is. Okay, and now we want to do evaluate late times, which is another function similar to early times, just reversing backwards. So it's gonna follow a similar format. So evaluate late times. Again, we'll use the same syntax. So we're going to say from the activity we're at to the next activity. And again, it's going to return none because it's just going to go and iterate and update the values internally. So we can almost copy and paste this check. So from activity, instead of 2, of course, we're going to go backwards. So we're going to have to look at the previous activities. From activities. There we go. Oh, I'm missing an I there. There we go. And now my spelling's going all over the place. There you go. From activities. We're going to return because we should be at the starter project now, because that one has no other from activities to go to. So we'll exit our evaluation. If not, if they've got some prior dependencies, we want to iterate them, so iterate through them. So as before, we'll call it the toActivity in from activity dot from activities, and we want to do if from activity dot late start time is less than or equal to the toActivity dot late finish time. Because the late finish times are all starting at like 99999, the late start time for the from activity should be lower, so we'll go, well, we'll need to update that. But of course we might be traversing and coming back across that node a couple of times depending on the multiple paths. So it's a check in case that actually it has been updated once and that late finish time is still earlier than my late start time, so that's the one that takes precedence. So toActivity dot late finish time equals from activity dot late start time, so it's going to take it as the value we're interested in. toActivity dot late start time equals from activity dot late start time minus the expected time again. So this is now we're doing exactly the same as before, where we were adding the expected time, but now we're moving backwards. Of course, we're going to be removing that down there. And as we're doing this, we've got the differences between the early and the late. We can look at the slack within the network, within the node, and if there's no slack, then we can identify that that is a critical activity. So if we do let's calculate. Let's do self.slack is going to be the toActivity early start time minus the toActivity dot late start time. Oops. There we go. And if it's not from activity. Apologies. There we go. So we calculate the slack. Let's just do if apps. It shouldn't, the late start time shouldn't come before the early start time unless we could flag that as an issue. But I just put the abs just in case here. We'd say if the from activity dot slack is less than, we're going to put a tolerance on this because of potentially numerical error building up. We'll just put a little tolerance there to say, okay, if it's very small, we'll consider it is critical. I mean, it could be smaller than this. It depends on how big or differently the activity durations are. Because we're looking at integers here. We've got quite large values, so anything that's smaller than that, it should be detecting as a critical activity. So yeah, if we're less than this, then we're going to say, this. Sorry, this should be the toActivity, not the from activity slack, of course. So toActivity slack. toActivity is critical equals true. So we're going to say that it is true. And then we can then do evaluate late times again. Because we've updated that activity, we might want to then proceed down with the updated values and see if it changes anything else down the network. So we'll just do evaluate late timed with that toActivity. So what we've actually done there is do the late start times finishes, but also we've started to highlight this idea of the critical activities and critical paths. We've computed those along the way. So if I just add that into our runtime here, evaluate late times SOP, no, EOP, we're going to start at the end of project this time, and then we can print we can print the SOP because that should be updated and should see highlighters as is critical. And actually, because we don't evaluate the EOP, we need to set this one. We know, of course, EOP is going to be critical. So this now should run and give us our late times. And as you can see, we've got a very small slack time. That's that numerical error that I was talking about, and it's propagated through on the late finish and start times. We have highlighted that it is critical, so yeah, because it's within our tolerance, and we're very generous with that tolerance. Then we've identified that, start a project obviously it's got to be one on the critical path, so it's kind of confirming that that's working. So now we want to do is try and identify the critical path nodes, or the critical activities. First of all, maybe we want to identify just the critical activities as a list, and then we can look at what ones are on the path. And in our case, they're going to be all on the path, but there might be cases where you've got parallel activities that happen to be also critical. There's no movement. If your network's very large, that might appear. So to identify the critical activities, we can just loop through the project plan. So for activity in project plan, dot values. If the activity is critical, then we can just let's print the actually we'll make a list of these then. So critical activities, and we're going to call that, it's going to be a list of string, and we're just going to append it first. Critical activities dot append activity dot key. Oops. Not activities visited. Oh, whoops, it's my spelling again. Append activity dot key, and we can print those out. So that'll print all the critical activities within. Oops, and I've misspelled activities there as well. There you go. Critical activities within our project. So if I run this now, here we go. So we've got our set of critical activities. And it should be A. It shouldn't be B. I don't know what B's popped up for. Or it looks like it's popped up every activity. Maybe that is a bit too generous on the error. Let's have a look. If activity is critical. Okay. So no, interesting. So it's declaring that all the activities are critical. Oh, whoops. My problem, my bad. It's calculating that one. It should be then the 2 activity there. That should be. There we go. So I was just miscalculating there with using the from activity slack rather than the 2 activity slack. So they should all be calculations on the next node. Should be using the from activity. So there we go. So we've got the ACEGEOP. So that is our critical activities. So now the final thing would be to compute the critical path. So to do that, we are going to create another function called critical path. Let's put it. Oops. God. Yeah. There we go. And it's going to be a none again, so return that. Just bear with me, I just need to answer the door, and I'll be back in 2 seconds. Okay, let's get back to it then. So, yes, critical path. Sorry about that, just had to pop to the door. So yeah, writing the critical path, we just need to do is, again, we're going to have a path variable here, which is going to be, we're going to enter all the keys for our critical path by, again, traversing and identifying the keys that are that we can proceed to that have been identified as critical. So we need the path, that's a string, and we're going to do we're going to again have an activity that we are coming from, and we're going to go to. So we just call this one activity this time, and we want to we're going to either give it a union. Oh, here we go. Of list of a string if it's identified, the path, or it's going to return a none. So we're going to have a series of nones where it may have gone down a set of critical activities, but it never reaches the start of project. So we just need to import the union type from typing. All right, scroll back up here. So the critical path. So what we're going to do is the path dot, because if we've moved forward in the critical path, we must add it to the path variable. So activity.key. If let's say if the activity dot key equals end of project, so if we reach the end, then we can return that path as a valid starter from start of project to end of project, valid critical path. Next up is for the two activities in activity dot two activities. If the two activity is critical, yeah, then we can say, okay, we want we want to then call this function again. So we've identified another critical activity, we'll move to that node, we'll do this again and see if there's got any critical activities on that node, and we'll move that again. So we just need to call the critical path function again. We'll do path.copy, give it a copy of the path it's now reached, because we might need to do it multiple times because we've got multiple activities to go to. And we're going to pass it the two activity variable to loop through. And if out exists, then we're going to return out. So if it doesn't return none, then we're going to return that one, because we have also found a critical path. So there may be multiple, but more than likely it's only one. If not paths were unsuccessful, we will return none at the end of it. So that's our critical path, again, recursive function. Now it's just a type to call that function, and then we're going to call it with the starter project. It's going to traverse through the graph and the project plan, and then it should either return a list of potential critical paths, most likely one, or none at all. So there might be that we've done, again, it'll be something to debug if we haven't got one, and we'll print that one as well. So we'll do print CP, and we'll print critical path above that. And if we run this code now, yep, we've identified it. It is the same as the critical activities we found, because we haven't got any additional critical activities. We've got the order there, so yeah, as well. Start of project, ACEG, end of project, and that is our critical path for this example. So hopefully this was useful. It was a good showcase of what you can actually do in Python to create your PERT model, and there's so much more to this type of analysis. So going forward, there's no reason why this method, you can't handle hundreds or hundreds of thousands of tasks, do very difficult, very large scale project plans. You can then run Monte Carlo simulations where we vary those task times, rather than just define one expected time. We could run it with lots of variations and see what the distribution and likelihood of tasks of the project plan completing on time is. We can look at identifying the stability of the critical path, because if we're varying those times over that Monte Carlo simulation, our critical path might change. So we might want to look at the occurrence of which paths are most likely to be the most critical ones, and if there's a couple, we might want to keep a closer eye on those paths in those larger projects. We can also set resource availability and limits and constraints, so we can't do so many parallel tasks at once, which might further push project activities back. We've only been using the time axis as one there. And ultimately, doing all of these types of studies on your project plans is all about helping mitigate and manage risk and uncertainty, and being more concrete about the likelihood of a project completing and when it is likely to complete. So hope you found this tutorial useful, and I'll see you in the next one. Cheers.